Hello, this is CS598 and I will be talking about the Shark file system. This is the agenda. I will be talking about I will give a little introduction, talk about the design of the file system, and end the presentation with some graphs and results that the research paper writers collected, and with a little conclusion. The current network file system have one big issue, and that issue is scalability. As more and more clients connect to the server, obviously the server becomes more and more overloaded. And even though peer-to-peer seems to fix that problem, peer-to-peer becomes more and more harder and harder to implement. So the best solution was Shark, that uses cooperative caching to improve scalability, and Shark is also secure, so it seems like a really great file system. Now the design. So the design works in the following manner, and this is the high-level description. Suppose you have a client that initially connects to the server and requests a file, and suppose no other clients have requested that particular file. So obviously there's nothing else to do but just grab the file from the server. Then the client caches the file and registers itself as a proxy in the distributed index. Also, the distributed index is called Coral, which I will talk about later. Now, when another client tries to fetch the same file, it'll look up in the distributed index and will take the subset of all the possible clients. Now, the reason why I say subset is because there is locality, so we don't want nodes that are really far away and deal with them. So in this case, if we have even if let's say we have multiple clients that have the same file, it will be very convenient because that client will be able to connect to those multiple clients and download different chunks of that same file in parallel. And once that client is done downloading all that, it caches that file and then registers itself as in the distributed index. And the two main functions that we need to worry about are put and get, where put makes the client request a file, and put is sending the file that is cached. Now the file servers. It uses a self-certifying path name, just like SFS, and the path name is right here, as you can see, and it's also very convenient because it's very similar with NFS. This is good since administrators will be quite familiar with the system and deployment will be less painful. The only difference between NFS and Shark is that communication with the server performed under secure connection. Now, file consistency. So there are two techniques that Shark uses to improve performance and reduce server load. So it has leases and EFS style whole caching. The most important one that I'll talk about is leasing. And what it does, part of it is to make sure that the file is up to date during the period at which the lease is issued. So once the client makes a read RCP to the server is committed during a certain period of time of notifying of any changes made to the file. So if a user attempts to read from a file, and if the file is cached and its leases are expired, and so no notification has been received, the read will succeed. Otherwise, if the lease hasn't expired and you get a server notification, then you will update the file. And the best way of doing the update of the file is, instead of getting the entire file, it'll only download the chunk that has been changed, which would actually cause a problem because there is a possibility of getting a mix of old and new file chunks, so you might get a file that is not quite what you want. But AFS style whole file can fix that by overwriting the entire file. Now, cooperative caching. This is the most important part. So, as I mentioned, the big picture of cooperative caching is this. Once the client requests a file and receives it from the server, it caches it. Now, the good part of this, the other client will not have to worry about getting the file from the server. So this will greatly reduce the overload of the server. So get toke supplies a file handle, offset, and account as argument, just as is in read RPC. So, but this one returns the file's attributes, the file token, a vector of chunk descriptions. And each description identifies specific extent of the file by the offset and size and includes a chunk token for that extent. And the server only returned up to 1024 chunk descriptions, so more and more of these calls will have to be made in order to deal with much larger files. So now exploiting file commonalities. So we described the chunking method by which I can leverage file commonalities. And this method uses the Rabin algorithm, which means instead of just dividing up the file into, let's say, certain size that are given, it chooses its own breakpoints based on the file contents. To divide file into chunks, it has to examine the overlap of 48-byte region, and it uses and based on that it decides whether a certain section of the file belongs to one chunk or the other. Now, distributed indexing. This is used for holding the nodes that have certain cached files, and it uses Coral as the distributed index. There isn't a lot of detail in this paper about what Coral is, so I guess we'll just have to deal with the name. And now what the client will be doing is it will execute a get on a certain index to get that file, and some proxies, and like I said, not necessarily all, it's all about locality. It wants the closest, the clients that are very, very close, and they perform a put under the given index. And stop if the once you're routing to the closest nodes, you'll either stop if you find the closest nodes, or you'll stop if the node is full. In other words, it has reached the maximum number of values for the key, or it has been loaded when there's heavy write traffic for a particular key, rather. And locality is based on which overlay cluster, and I'm sorry, this is a typo, this is supposed to be overlay, not overlay. And each region of the overlay cluster is called the diameter. So the implementation that has been used for testing, you have three daemons. You have the server-side daemon, the client-side daemon, and the Coral-side daemon. And all of these were implemented in C++, and you can even look at the architecture on the bottom. I'm not sure if you'll be able to see it right now, but you can look at it at the paper by zooming in. And what the shark-side daemon does is it's implemented as a loopback client, which communicates with the kernel NFS server. And essentially, it's an NFS, but it's a better version. The client forms is the big picture here. It's the biggest component here. It has to handle user request, and it also has to worry about caching. It also has to worry about caching and sending the files that have been requested, that also been requested by other clients. And the curl is just simply distributed index, so there's not much to talk about it. So now the evaluation. So of course, as part of research, tests have been ran, and these are the parameters that have been these are the machines that have been used for testing. So in the micro benchmarks and the Planet Lab experiments, you have the 1.4 gigahertz Athlon at New York University, OpenBSD 3.6 and 512 megabytes of RAM. The clients used Fedora Core 2. The Emulab tests were ran in the Emulab testbed, and they were all ran at Red Hat Linux 9.0. And also, these are the things that were considered. You also have two cases in Shark where it uses sequential requests or at random, and there is no negotiation. So in other words, clients may not reuse connections with proxies, and it cannot download multiple chunks once it's connected. So only one chunk per client. So you have these two graphs, the top and bottom one, and both of them are, the top one is the local area micro benchmark, and the bottom one is the wide area benchmark. And these, all of the graphs show the execution times in seconds, and it doesn't seem like in this case that Shark showed very good results. However, this graph shows a different picture in terms of client latency. So as it's getting a certain file, notice that the Shark random and when it has negotiation, it has a much steeper graph. So as time keeps going, it'll get a file much faster. But notice that the random without negotiation works as well with the same, and it's also the same case with the Shark sequential. And notice that it's the case with the 40 megabyte file as well. And I'm sorry, just to be clear, this is a 10 megabyte read and this is a 40 megabyte read. So you also have the Shark random with negotiation beating everybody. Well, the SFS is pretty linear, and notice that it's very slow. And this is the proxy bandwidth usage on the Emulab machines for 40 megabyte files and 10 megabyte files. So this is the client latency for 185 hosts who finish reading a 40 megabyte file, and this is between Shark and SFS. So obviously Shark is much faster, whereas SFS is extremely slow. It takes a while until you receive the entire file. And the proxy bandwidth usage keeps getting lower and lower on the Planet Lab when you're reading 40 megabyte files, because obviously more and more clients have cached files. It's the same situation right here. It's going lower and lower because you have more and more files cached. And this is where you see the normalized bandwidth on 185 hosts with 40 megabyte files. So 185 hosts try to read, all of them try to read the 40 megabyte file. You'll have the SFS will simply have 185 megabytes times 40, so it will be using 7,400 megabytes, which is a lot. But with the test performed by Shark, it only uses 954 megabytes, which is a huge drop. So in conclusion, Shark might actually be a really might, does have a chance of becoming one of the mainstream network file system, and hopefully this will be the case and it will not disappoint any of the users.